The pitot-static system. The pitot-static system is connected to the airplane's altimeter, airspeed indicator, and the vertical speed indicator. These instruments tell the pilot how high they are, how fast they are going, and how fast they climb or descend. These are determined by measuring the pressure of the atmosphere. Before we go any further, let us become familiar with the atmosphere. If we take a column of air, starting at the ground, and traveling up all the way into space, you notice that the molecules of air at the Earth's surface are much more compacted together than the molecules up in space. The reason for this is gravity. Since air is matter, it has weight. So, all the air molecules at the top of the column are pushing down on the molecules below them, which compresses them. This compression results in a higher pressure at sea level compared to the pressure on top of a mountain. How much of a pressure change are we talking about? Well, if we say the atmosphere goes up to about 375 miles above the surface of the Earth, 50% of those air molecules would be found in the first 18,000 feet of the surface. So, because the pressure of the atmosphere decreases the higher up we go, our pitot-static instruments are able to measure that pressure and calculate our altitude and speed. The pitot-static system gathers its pressure information from two sources, the pitot tube and the static ports, hence the name pitot-static. The pitot tube is designed to measure the pressure of the air as the airplane flies through it. In most smaller aircraft, this tube is located under the wing so it can measure the flow of air without any interference. Sometimes aircraft manufacturers will use a pitot mast instead of a tube shape, but it still functions exactly the same way. On the backside of the tube, there is a drain hole, which allows any rain or water that is collected while flying to drain out and not go into the system. Finally, the pitot tube can also be heated. This is used to prevent ice from forming on the tube, which could potentially block the hole and prevent the system from functioning correctly. The counterpart of the pitot tube is the static port. The location of this port will vary with different aircraft designs, but should be in a location where it can measure the static pressure of the air, unaffected by the dynamic airflow around the airplane. On the Cessna 172, the static port is located on the left side of the forward fuselage. The pitot tube and static port openings are connected to tubes that join into the pitot-static instruments. The pressure inside the instruments match the pressure of the outside atmosphere. All three pitot-static instruments connect to the static port, but only the airspeed indicator connects to the pitot tube. Sounds simple, right? Let's discuss how each pitot-static instrument works. Altimeter. Perhaps the most basic of all pitot-static instruments is the altimeter, which displays the airplane's altitude. The instrument contains a set of aneroid wafers which expand and contract based on the pressure. The air inside the wafers is trapped, but the air in the rest of the case is able to change to match the pressure from the static port. As we increase altitude, the static pressure goes down. This means that the air inside the case will escape out the back and result in there being less air pressure in the case compared to the wafers. Because of this, the wafers will expand until both pressures are equal. Getting the wafers to result in an altitude readout is done through the series of gears, pinions, arms, and levers, also known as the mechanical linkages. These linkages will rotate the hands on the face of the instrument and show the airplane's altitude. Now, when the airplane descends, the opposite happens. Descending to a lower altitude results in higher static pressure. Air from the static port will now enter the case of the instrument and squeeze the aneroid wafers until both of the case pressure and the wafer pressures are equalized. The mechanical linkages will then rotate the hands on the face to show a lower altitude. The face of the altimeter contains three hands, the 10,000-foot, 1,000-foot, and 100-foot hands. These hands move clockwise and counterclockwise to display the appropriate altitude. Most altimeters in smaller aircraft will only work up to around 20,000 feet, but those airplanes usually can't get that high anyway. Here's some examples of altitudes. 3,000 feet, 8,400 feet, 12,000 feet, 5,280 feet. This altimeter is actually called a sensitive altimeter, not because you have to hug it every once in a while, but because it can be adjusted for the current atmospheric pressure. Because the pressure at any given point on the Earth never stays the same, altimeters would always read incorrectly. Fortunately, pilots can correct this issue. Once the pilot knows the current atmospheric pressure, also known as the altimeter setting, all they have to do is rotate the dial on the lower left side of the instrument until the current pressure is selected in a little window on the face, called the Kollsman window. This then realigns the gears inside and the instrument reads accurately. The realignment is accomplished by rotating the entire inside mechanics of the instrument. Vertical speed indicator. Another instrument that uses only the information from the static port is the vertical speed indicator, more commonly called the VSI. The VSI measures the vertical speed of the aircraft in terms of feet per minute. This is accomplished by comparing the current pressure of the air with the pressure of the air from a few seconds ago. Inside the VSI is a diaphragm connected to some mechanical linkages that move the needles on the face of the instrument. The diaphragm has a direct connection to the static port, meaning that the pressure inside of it matches the current atmospheric pressure from the outside. The case of the instrument is also filled with static pressure, but the connection between the case and the static port is constricted by what is called a calibrated leak. This calibrated leak is nothing more than a tiny hole, which limits the rate at which the pressure of the case can change. When a plane climbs or descends, the diaphragm pressure will change instantly, but the case pressure changes slowly. This results in two different pressures. The difference in pressure allows the instrument to display the vertical speed. Be aware, however, that it takes a few seconds to read accurately, so anticipate a slight amount of lag. Here's an example of how it works. Say you have a Cessna flying at 3,000 feet. The air pressure in the diaphragm and the case are the same, so the VSI is reading 0 feet per minute. If the Cessna starts to climb, the air pressure in the diaphragm is decreasing, but the case pressure is decreasing more slowly. This results in the case having a higher air pressure than in the diaphragm. This higher air pressure will squeeze the diaphragm and make the VSI read a climb. Once the aircraft levels off again, the case pressure will finally equalize with the diaphragm, and then the VSI will show 0 again. Airspeed indicator. The airspeed indicator is the only pitot-static instrument that uses both input from the static port and the pitot tube. The pitot tube is used to measure what's called ram pressure. The faster the airplane travels, the greater the ram pressure is. The ram air entering the pitot tube gets sent to the airspeed indicator and, similar to before, goes into a diaphragm. The greater the pressure, the more the diaphragm expands, so the diaphragm will expand as the airspeed increases. Then, through mechanical linkages, the appropriate airspeed will display on the front of the instrument. But what about the static port, you ask? Well, remember how the pressure of the atmosphere changes with altitude? Well, if this wasn't taken into account, then the airspeed would indicate different speeds at different altitudes, even if the plane was actually going the same speed. To fix this, the static port connects and fills the case surrounding the diaphragm with static air. This will subtract out the static air pressure that the pitot tube captured and only allow for the dynamic pressure to be read on the instrument. This keeps the airspeed indicator reading the correct values no matter what the altitude of the airplane is. The face of the instrument displays color-coded speed ranges that the pilot should be aware of while they fly, to avoid exceeding any limitations of the aircraft. The green arc is for normal operations. The white arc is when you're allowed to extend the flaps. The yellow arc is limited to flight in smooth air only, and the red line indicates the maximum allowed speed.